Welcome back to Applied Mathematics. In this video, I want to introduce you to sets of numbers. The idea of a set is one of the most general ideas that we have in mathematics. Mathematicians in the early 1800s were trying to come up with the most abstract, generalized thing they could come up with to use as the foundation of all of the mathematics that was known at the time, and this definition is what they came up with. A set is a collection of objects which we call the elements of the set. The elements of a set can be literally anything, and all we're going to do is throw them in a bag. There's a couple of different ways that we can describe what is in a set. We can describe the collection. The simplest is roster notation. So if I want to build a set, let's go ahead and give it a name. I'll call it set A because I'm not very inventive. Well, to list out the elements of a set, you're going to start with some curly braces. The curly braces in this context are referred to as set braces. And then you're going to list all of the elements that are on the roster of the set. So maybe this set contains the word chair, and it contains a picture of a chair, and it contains a blue swatch. Right? What does that actually mean? I don't really know, and quite honestly, I don't really care. We have this thing. It is called a set. We have things in it. The word chair. Anytime the word chair appears anywhere in the world, that is referring to the chair that is in this set. We have a picture of a chair. Does that mean just my poorly drawn picture, or does that mean all pictures of chairs, or is that supposed to represent all actual chairs? It's not clear, and I'm not interested enough in order to clarify. What I am interested in, if I get my head out of the way, is making note of the fact that in roster notation, or really in any context, a set is an unordered list. That is to say, I could shuffle my elements of my set around. I could put picture of a chair first, then my blue squiggle, then the word chair, and that's the same set. There's nothing about one or the other that makes it preferable in general. There might be some context in which a particular order is more useful, but that's not really what's important. Although this video is called Sets of Numbers, so we're not going to worry too much about these abstract cases of sets. We're going to focus on the real heart of the matter. We will start off with the natural numbers. Whether or not you've come across this vocabulary before, this set is the one that you started out with. This is the first set of numbers you were ever introduced to. Some people also refer to this as the counting numbers. But we like the natural numbers because mathematicians use the symbol of a letter N, although it's a bit of a strangely drawn N. It has that extra line in it. We call this a double stroke or a blackboard bold N, and it's meant to stand out. You're not really going to have to write that symbol at any point in this course, but you should be familiar with it because it will pop up from time to time, and you should be able to recognize, oh, it's a funny N. That means we're talking about the set of the natural numbers. Right? But the set of the natural numbers are the set of numbers that you first learned to count with. 1, 2, 3, 4, and it keeps going, but I don't want to have to write out all of the numbers forever, so I'll use ellipses to say we keep going with this pattern. In the United States, we have a very closely related set called the whole numbers. The whole numbers take this set of natural numbers and simply introduce a 0 to it. I tend to think of the whole numbers as the counting numbers according to a computer scientist, because in most computer science applications, counting from 0 makes things a lot more sensible than counting starting at 1. When I introduced this, though, I said in the United States. We are already at a place where there is significant controversy and inconsistency in the mathematical community. In different languages and in different cultures, instead of calling this the natural numbers, very often this will be called the natural numbers instead. Specifically, I know that in French, they use the blackboard bold N to represent this set. That makes things confusing. That makes things a little bit tricky. Really, the takeaway is you have to be careful. For our purposes, I'm not really going to worry about it. Whether 0 is a natural number or not is not going to make any difference in anything we do in this course. We really don't have a symbol for the whole numbers, but just for the sake of argument for right now, I'm going to go ahead and call it W, so that we can talk about the next idea. The next idea is called a subset. A subset is a set where every element of the first set is also an element of the second set, but they are not the same set. In this case, I want to point out that the natural numbers are a subset of the whole numbers. Every natural number is also a whole number. There happens to be one whole number that is not a natural number, specifically 0, so it would be wrong to say that the whole numbers are a subset of the natural numbers. In most cases, with most sets, neither of those relationships are true. Right? For another example, if you have the set 1, 3, 5, and you have the set 1, 2, 3. There's an element in 1, 3, 5 that is not an element in 1, 2, 3, and there's an element in 1, 2, 3, 2, which is not an element in 1, 3, 5. So in that simple example, neither of these are a subset of the other one, which kind of goes to show how useful subsets actually are. All right, but we have the natural numbers, we have the whole numbers, and with just those two sets of numbers, we can do a lot of mathematics. All of addition works perfectly fine. 3 plus 4 is 7, and 7 is also a natural number. Multiplication also works fine. 3 times 4 is 12, and 12 is also a natural number. But if you try to get a little bit beyond that, subtraction, for example, stops working. 7 minus 4 is 3, that's fine, but 4 minus 7 is negative 3, and negative 3 is not in this set. So in order to continue and be able to do subtraction, we need to develop a bigger set of numbers. That bigger set of numbers is called the integers, which sometimes you'll also see referred to as the signed numbers. Or for someone who wants to be really pedantic, the signed whole numbers, but I've never seen that in practice. The symbol for the integers is a double stroke Z. Why Z? The best I've been able to ascertain is the idea of sets of numbers were first being developed by German mathematicians. At the time, all of scientific discourse was run through Germany. And in the German language, the word for number starts with Z. So that's what they went with. But the signed numbers I'm going to write in this format with ellipses going in both directions. So continuing onward forever, eventually we get to -2, then -1 and 0, then 1 and 2, and continuing onward forever. This configuration is supposed to elicit ideas of a number line. So we can think about the integers on a line continuing onward in both directions. That's really great. Another thing that I want to point out is that the natural numbers are a subset of the integers. Every natural number is also an integer. There are a lot of integers that are not also natural numbers. And yes, the whole numbers are also a subset of the integers. I'm not nearly as interested in that fact. While I'm talking about integers, there's a new operation that we can come up with. Yes, of course, subtraction suddenly starts working. We can subtract two positive numbers and maybe we'll get a negative result. We can subtract a positive and a negative number. We'll get into those ideas in a little bit later. But with the integers, we have a new operation called absolute value. The notation of absolute value is vertical bars, and I'll go ahead and call this the absolute value of x. The definition of absolute value is the distance from x to 0 on a number line. The key idea in this definition is that absolute value is a distance. And distances are always positive. You cannot have a negative distance. If you don't believe me, I invite you to build a table that's -5 feet wide. If somehow you are able to, I can probably swing a $1 million prize for you. I just ask for a 10% finder's fee. So absolute value, whether the thing you put into it is positive or negative to start, always is going to give you a positive result. The absolute value of 7 is 7, and the absolute value of -7 is also 7. Nothing too crazy going on there, but that idea of being able to get a positive result out can be very helpful in a lot of contexts. So it's worth remembering that it exists. All right. But at this point, we have addition, subtraction, and multiplication all working fine. The next operation that could be a problem is division. And to come up with a way of dealing with that, we need the next set of numbers, which are called the rational numbers. Sometimes also referred to as fractions. The symbol for the rational numbers is a double stroke Q. Why Q? Well, first of all, we need R for something that's yet to come, so we couldn't use R here. The next set is also going to start with an R, and it is definitely more important. But the idea here of Q is actually from the word quotient. Remember that quotient is the result if I can write. Okay, I can't write in the first place, but the quotient is the result of doing division. So when we divide two numbers, the result is a quotient. And sometimes that quotient will be a whole number, sometimes it will not, which leads us to the fractions as another way of dealing with it. Writing out all of the fractions is incredibly challenging. There's no nice pattern that we can use to list them all out. So instead we have to resort to another notation. Known as set builder notation. We're going to start off with a set brace just like before, but instead of just listing out things, we're going to use some variables to construct a prototype. In this case, the prototype is going to be P over Q. And then we're going to put a vertical bar, and we're going to describe what this prototype is doing. In our case, we need to have P is an integer and Q is a natural number. This is perhaps the only place in the course where we're going to be very happy about the fact that our definition of natural numbers does not include 0. Because if we included 0, then all of a sudden we would be dividing by 0, and as you know from your previous study in mathematics, dividing by 0 can cause problems. But the way we read this, the set of all fractions P over Q such that P is an integer and Q is a natural number. I think learning to read that vertical bar as the phrase such that is kind of the key here. I'll also mention quickly that in a lot of contexts, you'll see a colon instead of a vertical bar for that. The reason for that is that there are a lot of contexts involving set builder notation where you need absolute value. And so mixing the vertical bar for set builder notation and the vertical bar from absolute value can get confusing. So having a couple of different options is certainly useful here. Right? But for our purposes, this is good enough. Any fraction, we can take any signed number and put it in the numerator. We can take any natural number, any non-zero counting number, and put it in the denominator, and we have a fraction. Some of the things that come away from that, well, I can take 7 over 1. And of course, we know that 7 divided by 1 is just 7. So I can take any integer and rewrite it as a fraction, which gives me that the set of all integers is a subset of the set of all rational numbers. Of course, one of the downsides of working with this definition is that it actually multiply defines every rational number, because 7 divided by 1 is 7, and 14 divided by 2 is also 7, and 21 divided by 3 is also 7. All three of those, 7 over 1, 14 over 2, 21 over 3, are rational numbers according to our definition. In order to avoid confusion, the convention in mathematics is that whenever we refer to a fraction, we must reduce the fraction to lowest terms. We must set up so that there's only one correct way of representing a fraction. There are several different notations that I've seen people use for reducing fractions, but if I have something like, I don't know, 28 over 35. You may notice that 28 is 4 times 7 and that 35 is 5 times 7. There's a common factor of 7 that you can cancel out. And when you cancel those out, you are left with 4 over 5. Or if you have a calculator that is capable, such as this one, right? I am not sponsored by Texas Instruments. I don't specifically care that you use this particular calculator. It just happens to be the one that I have that has a nice fraction key on it. The fraction key in this case is right above the 7. When I push it, it gives me something that looks like a fraction. If I type 28 into the numerator, and then I use my arrow keys to navigate down to the denominator and type 35 and hit enter, it reduces the fraction for me. Calculators are powerful and are able to do most of the things that we're going to be doing in this class, but not all of them. And so I want to stress before we go any further that a calculator is a powerful tool, and there are definitely going to be times when we need it. But as you're watching me go through some of these tricks using pencil and paper, I want you to take the time and do the same. This is going to be a building block for you. Yes, my calculator can do this without me having to think about it. But because I know how this works, when we get to more complicated things a little bit later on in the course, or especially if you continue on to the next semester of this sequence, it will already give you that initial step that you need in order to look at things that your calculator is not able to handle on its own. The other thing we have to worry about in dealing with fractions is mixed numbers and improper fractions. This is a place that instills a lot of confusion. I know there's a lot of instructors who try to say that mixed numbers are the one true way and you should never write improper fractions. There's also a somewhat smaller subset of instructors who say that improper fractions are the correct way and you should never write mixed numbers. The real answer is it is entirely context-based. There are situations where a mixed number makes sense and an improper fraction is very difficult to work with. There are places where an improper fraction makes sense and a mixed number is very difficult to work with. In this course, we're going to look at very few places where mixed numbers are useful, not to say none, but very few. We're going to look at a lot of places where improper fractions are useful. So if I have a mixed number, let's say something like 3 and 3/8. Well, the way to think about a mixed number is that it's really addition in disguise. 3 and 3/8 is 3 plus 3 over 8. And we'll talk more about adding fractions later, but one thing that you should remember is that to add fractions, you need a common denominator. When you have a whole number, that's actually pretty easy. What do you divide by 8 to get 3? Well, if you just take 3 times 8, 3 times 8 is 24, that tells you that 24 divided by 3 is, 24 divided by 8 is equal to 3. And now by having done that, we have that common denominator. We can add in the numerator and we'll get 27 over 8. If we have an improper fraction and we want to create a mixed number out of it, well, in this context, we're going to be doing some division. How about 625 divided by 28? I'm not entirely sure what application would have a 28 in the denominator, but we can go with it and it will work. In order to turn this improper fraction into a mixed number, we're going to set it up as long division. 28 goes into 625. And when we're working with long division, remember we go one digit at a time. 28 does not fit into 6, but it does fit into 62. And in fact, it fits into 62 twice. 2 times 28 is 56. If you subtract 62 minus 56, you get 6. Drop down the next digit, which is a 5. 28 fits into 65, coincidentally also twice. 2 times 28 is still 56. Subtract off this time, and you're going to end up with 9. That remainder 9 is going to become the numerator of the fraction. So our whole part of 22 and our fractional part is going to be 9 over 28. The denominator of the fractions is the same denominator as the fraction you started with. Right, one quick trick on this problem. I don't want me, I want my calculator. There we go. My calculator can't really handle mixed numbers. If I try putting in 625 over 28, it just still gives me 625 over 28. But it will give me a decimal approximation. The decimal approximation key on this calculator is right above the enter sign. It is kind of a squiggly thing, right? That squiggly equal sign is the mathematics definition, or the mathematical symbol for approximation. And it gives me 22.32, etc. That's not quite what I want, but it actually gets me a lot of the way. Right, let me set up this long division again. I wanted 28 fits into 625. If I ignore the decimal part and just keep the whole part, 22, then I continue my process as always. I'm going to multiply 22 times 28. My calculator tells me that that's 616. And then I'm going to subtract. 625 minus 616, my calculator tells me is 9. That's my remainder. 22 and 9 over 28, the same thing I got, a little bit less painful by using our calculator to our advantage. Right? Even though the calculator cannot take the entire process off of our hands, it can take a little bit of it, and every little bit helps. Before I move onward, I do want to at least talk a little bit about why and how. We have mixed number notation, we have improper fraction notation. How do we determine which one is more useful? Well, the question mostly comes down to, what else are we going to do? If we are trying to find a number as part of a calculation, and we're going to do more calculations later on, an improper fraction is almost always the right way to go. If we are trying to answer an applied problem, if we have some real-world situation that we have turned into mathematics, we have done work on the mathematics and we've come up with a numerical response that we're trying to use as our answer to the situation. That's where a mixed number tends to be the most useful. So if there is an applied situation where a fractional value written as a fraction and not a decimal is the correct way of answering it, then giving that answer as a mixed number is going to be correct. In any other situation, we're going to go with an improper fraction. An improper fraction is going to be more useful to us when we are trying to do calculations. Trying to do any operation other than addition on mixed numbers is incredibly painful, and I'd rather not, so we won't. And for algebraic problems where it's just, here's the result, we'll leave things as an improper fraction because we don't know what the purpose is. We don't have any way of interpreting our result in terms of the problem at hand, so there's not really anything else for us to do. If the instructions don't specifically say to use a mixed number, and it's not an applied problem that you're giving an answer that makes sense as a mixed number, improper fraction is going to be the way to go. That's going to be my convention. We're going to be using the improper fraction as our calculation tool anyway. That's going to be the form that the number is in when you get to the result, so save yourself the step. Don't try to turn it into a mixed number unless you have to. All right. I think that's enough said about fractions. There is one other set of numbers that I want to talk about today, and that is the real numbers. The symbol for the real numbers is a double stroke R, or a blackboard bold R. And the real numbers are going to be our default set. Unless we have reason to assume otherwise, we're going to assume that every number we work with in this course and in any other math course you ever take is a real number, and we don't know anything else about it. You'll notice that I didn't even try to write out the set, because it's practically impossible. Instead, I'm going to give a couple of characteristics. If you're really curious, if you continue onward in your studies until calculus, we can finally at that point define a real number, but for right now, I'm just going to give you the broad strokes. Every rational number is a real number. There are also what are known as irrational numbers, and there are two types of irrational numbers. All right, so irrational numbers are also real numbers. This includes algebraic numbers, algebraic numbers are things that we can define pretty nicely, but just don't have nice calculations. So things like the square root of 2 or the cube root of 35 are irrational numbers that fall under the umbrella of algebraic numbers. If I jump to my calculator one more time here, and I try to calculate the square root of 2, my calculator just tells me it's the square root of 2. But if I hit that approximation key, it gives me this ugly decimal result. There is no way to write this as a fraction. That's just all we have. It still counts as a real number. The other kinds of irrational numbers we have are called transcendental. A couple of examples of transcendental numbers. Pi. Right, pi is 3.14. That's probably something you've been forced to memorize at some point in your previous study of mathematics. If I turn to my calculator, it gives me a few more digits. I have a pi button right here. And if I hit the approximation key, it's going to give me out to 3.14159.265. And then the next thing it gives me is a 4, which is actually rounding, because if you continue on the decimals, you actually get 358979323 and more digits from there. One of the common tools used for calibrating supercomputers is finding out how fast it can calculate 1,000 digits of pi or 1,000,000 digits of pi or something like that. One of the things I always love to point out is if you go that far, right, I think I counted that out right, that's 12 digits. That's how many digits of pi NASA uses when they do things like the New Horizons space probe, which in 2015 flew by Pluto. based on their calculations using that much of pi, they were able to calculate how to fire the New Horizons space probe on a rocket out of Earth and send it floating through space for 10 years to the outer edge of the solar system. And it was about 10 feet off course and 5 minutes early. So there's the level of precision you can get out of just that much of pi. We'll talk a lot more about precision in coming weeks, but for right now, just a little bit of a fun anecdote. And I really like pi, so I'm going to talk about it more than I should every time it comes up. Another type of transcendental number is not nearly as useful. But if we do something like a weird pattern, how about 1.01,001,0001, 4 zeros and a 1? That's only 3. There's 4 zeros and a 1. Then 5 zeros and a 1, 6 zeros and a 1, 7 zeros and a 1, and so on. This decimal number is, well, first of all, atrocious. Second of all, cannot be written as a fraction. But it is still irrational. It still falls under the umbrella of the real numbers. All right. So we have all this stuff that is real numbers. I guess the question then is, what is not a real number? Well, what is not a real number is an imaginary number. An imaginary number involves the square root of -1. If you think about a square root, the square root asks you, what do you multiply times itself to get the number inside? The square root of 25 is 5 because 5 times 5 is 25. You could have also multiplied -5 times -5 to get 25. But there's nothing you can multiply times itself to get -25, right? +5 times -5, but those aren't the same number. So there's nothing you can multiply times itself to give you a negative number, which means that if you have a negative underneath a square root, that's a problem. And that problem is severe enough that we're going to kick that out of the real numbers. The other thing that we're going to kick out are the transfinite numbers. The transfinite numbers are the things that happen when you try to divide by 0. Very bad things will happen if you try to divide by 0, the mechanics of which are well beyond the scope of this course. So for our purposes, just realizing that if it's an imaginary number, it's not real. If it's a transfinite number, it's not real. We don't have to worry about those because they aren't real. That's good enough for us. In those sets of numbers, I've followed this consistent pattern of I've built up bigger and bigger and bigger sets. We started with the natural numbers that were small. We got to the integers, the rationals, and the reals, which were just getting bigger and bigger and bigger. Now I want to kind of step away and look at things from a different perspective. Another thing that we might care about is whether a number is exact or approximate. One-third is an exact value. 0.3 is an approximation of 1/3. 0.33 is a better approximation. 0.333 is a better approximation still. But in all of these cases, I had to round at some point. Likewise, the symbol pi is an exact value. 3.14 is an approximation of pi. 3.14159 is a better approximation. 3.14159.265 is an even better approximation. But when we're dealing with an approximation, we are rounding. Later on in the course, in the coming weeks, we're going to look at how rounding affects things, where we choose to round, why we choose to round, other situations that are forced upon us. But for right now, just understanding, this is going to be our convention. If we have a number that's written as a fraction, we're going to assume that that represents an exact value. If we have a number that's represented by a symbol like pi, we're going to assume that that is an exact value. If we are giving a decimal value, we're going to assume that that is an approximation and that we've had to round somewhere. This can be a little bit tricky at times because, of course, the fraction 1/2, if you convert that to a decimal, is 0.5. I didn't round. There's no other digits that come after it. But I'm going to treat 0.5 as an approximate value and 1/2 as an exact value. This is going to be something that continues throughout the course. If you see instructions that say give an exact value, that means you had better give me a result that looks like fractions or symbols. And if you give me a decimal, that's wrong because you've given me an approximation. Even in this case, right, 1/2 works out exactly as the decimal 0.5, but our convention is that when we see 0.5, we're going to assume that it was an approximation because there's no context that I can give it that will tell me this was exactly 0.5. Looking at that, that also gives us another way of classifying numbers. Some numbers are actually written using numerals. We're going to call those denominate numbers. That includes things like 32, 3.5, and 1/2. We also had some symbols that were written using variables. We're going to call those literal numbers. That includes things like pi. That also includes variables like x. That's another one where the language doesn't quite make sense with how modern English is used. At the time it was first used, it made a lot more sense, but language drifts over time. If we have a symbol, we're going to call that a literal. If we have literal numbers, we're going to call that denominate, not literal. Later on in the course, we're going to be talking about literal expressions and literal equations. When we say that, we mean equations and expressions that have a lot of symbols and no numbers. Right. For right now, I think this video has gone more than long enough, so I'll wrap up with that. As always, thank you for joining me. I'll see you next time.